Hello and welcome to the third video of the M2 chapter Impulses and Collisions. Exam question on the screen to review what we've done so far. Three particles, P, Q and R, have masses 3m, km and 7.5 m respectively. Now because we're not going to do part C until video 5, we don't need to worry about R, we're just going to look at P and Q for A and B. The particles lie at rest in a straight line on a smooth horizontal table, with Q between P and R. So what we need here is P and Q. Q is going to be at 0 meters a second. Initially so is P, but then we see that particle P is projected towards Q with speed U. So as usual, I'll take this direction to be my positive, so this becomes U. And it collides directly with Q. The coefficient of restitution between P and Q is 1/9. Now take notice that this is between P and Q. Between Q and R, when Q later collides with R, the coefficient of restitution between Q and R could be something completely different, because it's specific to the pair of particles. Part A, show that the speed of Q immediately after the collision is this. So we go through our usual process. We need conservation of linear momentum to form one equation. Here, particle P is 3m, particle Q is km. So we've got 3m times u plus km times 0. And then after the collision, P is still 3m, call this v1. Q is still km, call this v2. So the equation on the right hand side is 3mv1 plus kmv2. Then we can simplify a little bit by cancelling the m's. And now I need a second equation because we have two unknowns here. The second equation is going to come from Newton's law of restitution. And from our previous video, we know that that is the speed of a separation, v2 minus v1. Remember, in this context, I can be confident that v2 as a velocity is greater than v1 because they've impacted here, and P will not continue to impact Q without something else going on. So that's the speed of separation. The speed of approach is just u, because Q is initially at rest, and that has to equal E, which we know is 1/9 from the question. A little bit of rearranging gives us v1 is equal to v2 minus u/9 as our second equation, which I'm going to substitute into here. So that's coming from there. Combining these two together, we get 3u is equal to 3 times v1, which we now know is also v2 minus u/9, plus kv2. A bit of rearranging here. Collect the v2's and factorize them out. Combine those two, gives us 10u/3 is equal to v2 3 plus k, and then divide through, and we get 10u/3 3 plus k as required in the question. Part B, find the range of values of k for which the direction of motion of P is reversed as a result of the collision. So if P is going to be reversed, we've had a similar question to this in the previous video. The key point here is that v1 is less than 0. If v1 is not less than 0, then the motion of P was not reversed. So that's our starting inequality, but we'll also need to know what is v1 in terms of u and k. And we can use our v2 here and the equation here to solve for v1. So putting those two together, part B, we know that v1 from the question must be less than 0 for the motion to be reversed, and v1 is also equal to v2, which we know is 10u/3 3 plus k minus u/9. So all of this expression must be less than 0. Now it's just a case of rearranging and solving for k. So if I bring u/9 on this side, 10u/3 3 plus k, the u's cancel, I can bring the 9 over here without a problem, and I can bring 3 plus k over here without a problem, because I know that k must be positive if it's a multiplier for a mass. We're not going to have a negative mass here, so 3 plus k must also be positive, so I don't need to worry about changing the sign of the inequality. I've got 30, 3 plus k, and here 27k. So k must be greater than 27. So that's a good question to summarize most of what we've done so far in this chapter. In this video, we're going to look at problems involving a direct collision with a smooth plane. And this is actually a little bit easier than what we've just done there in the starter question. So far, all the problems have involved two particles, but we need to be able to use Newton's law of restitution for a collision between one particle and a smooth fixed plane. In this situation, we don't need to use the conservation of linear momentum, because the plane will be fixed. To talk about conservation of momentum in this case, we would either need to know more about the forces holding the plane in place, or talk about the internal structure of the plane. We're not going to go that deep into it in this course. We're just going to assume the plane is fixed, it doesn't move, so none of the questions will involve conservation of linear momentum. In this situation, you just need Newton's law of restitution. Just in case it comes up, however, I will add one little note here, that the impulse on the particle from the plane will always be perpendicular to the plane. Most of the time, you can assume that without thinking about it, but let me just sketch out the situation where you need to be aware of this. So if you can imagine that we are looking down on a table, there's a particle on the table is horizontal and smooth as usual, and the particle is moving along the table towards a smooth vertical wall. Here's the wall, we're looking down on that as well. Then it's pretty obvious that as the particle hits the wall will exert an impulse on the particle that is at right angles to the wall. What might not be quite so obvious is if we have a similar situation, but the particle is not moving directly towards the wall normally, in the normal direction, but is coming in obliquely at an angle. In this situation, as the particle hits the wall over here somewhere, the impulse on the particle from the wall will still act at right angles to the wall. What this means is, if in an unlikely situation you had a question like this, you would have to split this into its component parts, perpendicular and parallel to the wall, and this part of the velocity would not change. It would not be affected by the impulse. Only the component perpendicular to the wall would be affected by this impulse. And you would probably instinctively understand that if we come after the impact and see that it's going in this direction, the fact that the particle is moving towards the wall changes and it's now moving away from the wall, but the fact that the particle is moving upwards on your screen would not change. So while I think it's unlikely you'll have to deal with this situation in M2, I just thought it was worth mentioning just in case you come across a question with vectors and this comes up. The examples in the rest of the video are much simpler than this. A particle collides normally, is that word saying it's perpendicular to the wall, with a fixed vertical plane. Before impact, the particle is travelling at 8 meters per second. So again, we're looking down from above. After impact, the particle is travelling at 2 meters per second. Find the value of the coefficient of restitution E. So the reason questions like this are easier partly is because you don't need to worry about linear momentum, but also because E, the speed of separation, is just how fast it's coming away from the wall after the impact, and the speed of approach is just how fast it's coming towards the wall before the impact. The wall will always have zero velocity. So E here is simply 2 over 8. Now if I was being very careful, I might say minus 2 here for the velocity, but it's still a positive 2 here for the speed. So E in this case is 1/4. Example 2. A small sphere collides normally, here's that word again, coming in at right angles, with a fixed vertical wall. Before the impact, the sphere is moving with a speed of 4 meters per second. On a smooth horizontal floor, the coefficient of restitution between the sphere and the wall is 0.2. Find the speed of the sphere after the collision. Again, we have e is equal to the speed of separation divided by the speed of approach. We know that e is 0.2, and we know the speed of approach is 4. Therefore, the speed of separation, how fast it's coming away from the wall after the collision, is 0.8 meters per second. Third and final example. A particle falls 22.5 centimeters from rest onto a smooth horizontal plane. It then rebounds to a height of 10 centimeters. Find the coefficient of restitution between the particle and the plane. This example is more involved. So initially, we've got the particle, the plane, and it is 22.5 centimeters above the plane, and it's starting at rest. Then later on, it has bounced, and it's come back up to a height of 10 centimeters. And at the very end, when it reaches this height, that is also at rest. But to find the coefficient of restitution, what we need is the speed immediately before the collision, after it's fallen down here, just before it hits the ground. We need to know what is that speed. That will be the speed of approach. And over here, we need to know the speed immediately after it's bounced, just before it starts coming back up. That will be the speed of separation when we're focused on the collision between the particle and the floor. So although we're not really worried about how it moves here as it falls or how it moves as it bounces back up, we do need to know that in order to find the two things we're interested in, the speed just before it hits and the speed immediately after it hits. And this is a constant acceleration problem. So on the left, we need to know what is v in this situation. S looks like it's going to be 22.5, but really we should put this into meters. Should be 0.225 meters. So I'm taking downwards as my positive. A is equal to G, which is 9.8 downwards, so that's positive as well. U is equal to 0. We want V, so the formula is V squared equals U squared plus 2AS. Putting in the numbers gives V squared is equal to 0 squared plus 2 times 9.8 times 0.225. And that gives us a final answer for V of 2.1. If this was considered a perfectly elastic collision, then I would expect this then to be the initial speed over here as it bounces back. But if we did that, it would bounce back to the same height, 22.5 centimeters. It hasn't, it's only come up 10 centimeters. That means the speed it has rebounded with is much less than 2.1. And the ratio between those two speeds, of course, is what we're looking for, the coefficient of restitution. So I need a completely separate calculation over here to work out what is u in this situation, although it's a very similar situation. We've got s is equal to 0.1 meters, a is equal to minus 9.8, because in this situation I'm taking upwards to be positive, v is equal to 0, and u is what we want, but it's the same formula. V squared equals u squared plus 2as. We have 0 equals u squared plus 2 times minus 9.8 times 0.1, which gives us a final answer of u as 1.4 meters a second. So we've got two very nice numbers here. I didn't round those. They came out as 2.1 and 1.4 exactly on my calculator, although we have of course used 9.8, which is a rounded number, to find E. E is equal to the speed of separation, which is the speed immediately after the collision here, 1.4. That goes in the numerator. Divided by the speed of approach, that's the speed immediately before the collision here, 2.1, in the denominator, which gives us a coefficient of restitution 2/3 between the particle and the plane. And rereading the question, I can see that I haven't quite finished it, because that should be written to two significant figures, 0.67. I assume that's because we've used 9.8 in our calculations. I hope that's enough now for you to have a go at the questions in exercise 5C, and maybe I'll see you in the next video.